Have you been wondering what the heck that nature node is throughout the last few lectures? What is nature? How would nature be a node? What would it be for nature to assign a type or something like that? What would it look like for nature to assign a type? It's a reasonable question. You've just been sitting there accepting my word all this time. Well, I mean, that's what happens. This is nature. This is nature. Well, this isn't nature just yet. Let me show you nature in my hands. Nature. 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 Exogenous variation. Exogenous variation! Oh, don't even act like you're not going to miss this. Exogenous variation. I need to do it 7 times for it to be fully shuffled. Exogenous variation. Exogenous variation. Alpha. Hey everybody, welcome to PS 231. If you can believe it, we have made it to the final topic, capital F, capital T, in our class. Over the past few lectures, we talked about how to incorporate this very natural idea of incomplete information into our book of fables. And we've done this both in simultaneous moves, as with the musical companions or in that swing voters curse model, and in sequential games like in the pivotal politics and bargaining model of war versions that we've seen in lectures and problem sets respectively. For the simultaneous move versions, we extended our notion of Nash equilibrium to something called Bayesian Nash equilibrium, wherein every type of every player plays a best response. If there's 2 types of you, then they both get to condition what they do on what they know, and thus we think about potential profitable deviations type by type rather than player by player. In the sequential variants, we came up with something that had a subgame perfect flavor in the sense that there was sequential rationality. We went to the end of the game, figured out what relevant parties would do there, whether it's a player or just a type of a player, and then we worked backwards up to the top of the game. Both in the pivotal politics model that we studied and in the bargaining model of war that we slogged our way through in the problem set, the uninformed player moved first, right? So the person that had to make the offer, the proposer or country 1, they had to move first. They had to move in ignorance of what was going to be happening down the line. Consequently, their beliefs about what state of the world they were living in was determined only by the exogenous chance of one type or another, the initial prior probability, which we encoded as alpha. I think that there's an alpha % chance that we're in one state of the world and a 1 minus alpha % chance that we're in the other state of the world. And thus, when I make my expected utility calculations about what offer to make, which mountaintop to try to get to the top of, once we're doing that, then I just think about this only in terms of alpha. There's nothing that you can do, the informed player, I'm just proceeding as if I'm the ignorant one, which is probably the most useful default setting, right? There's nothing that you can do as the informed player to influence my beliefs about which state of the world that we're in, because you move last. But it doesn't always work like that, right? Sometimes informed players move first. And that means that uninformed players have to take what they thought might be true and couple it with what they observe, the choices that they observe made by informed players, the signals that they see. So the final topic, capital F, capital T of the class, is signaling, and we'll see a more explicit characterization of what's called perfect Bayesian equilibrium, where beliefs have to comport with actions, have to comport with beliefs. In other words, what is mutually reinforcing isn't just my choice and your choice, but rather your choice, how it influences my beliefs, and therefore informs what I think is best in expectation, which then in turn has to be something that you are best responding to. In other words, equilibrium combines time, information, and best response. We're going to take all of the elements that we've done since we got started with game theory in week 6. We're going to take best response, time, sequential rationality, and information in the sense of you only get to make one choice in an information set. We're going to take all three of those things and put them together into one beautiful, complete whole. We'll spend 2 weeks on this. We'll do a simple version of signaling today, and we'll do the canonical OG version of signaling next week. Signaling models are incredibly popular in political science because it's oftentimes the case that people have the opportunity to make a move once they know something is true, and other players have to observe what happened, right? Put differently, sometimes people bluff. Sometimes people pretend that they're in a good political situation when they're not. Sometimes they know that they have no power, but they have to act as if they do in the name of trying to act as if they're strong in the name of getting better bargained outcomes. Signaling. How do the choices that you make inform what I think about you? In order to introduce the logic of signaling to you, we're going to study the simplest possible signaling model in an introductory sense. We're going to study what's a model of poker, but it's going to be like the simplest poker game you've ever seen, and you'll see it's still enough to make you go completely batty. And it might seem trivial, and Lord knows I'm going to be choosing a Vegas-themed funky soundtrack throughout the entire lecture, so you might as well just get ready for that. It seems trivial, and yet it isn't trivial. You'll see that there's a lot of intrigue underneath this completely simple model of poker. And more importantly, there are many people that have compared important political processes to poker. Perhaps most canonically, the great military theorist Karl von Clausewitz referred to war as a game of cards, and he specifically meant a game of poker. There's bluffing, there's signaling, there's inferred intentions based on observed actions. You'll see that the style of analysis here involves poking at our poker model a little bit more. We're going to be sort of guessing and checking using the model as almost a plaything. You'll see that the model that we draw on the screen is going to be very manipulated. We'll be doing a lot more than just putting stars next to numbers. We will be playing with this model that's in front of us, which, I don't know, I think that's pretty fun. It might make you a little bit dizzy depending on how awful the animations are this week. So we've got an awful lot of lecture to get our way through, and I think it's going to be a super fun one. And so I don't want to issue any more delays. I want you to get comfortable. I want you to get locked in. I want you to get some liquids. I want you to get yourself everything that you need to be prepared to win every game of poker that you'll ever play for the rest of time. That isn't true. Don't listen to me. Let me call some lawyers. Disclaimer. You're not going to win a poker, and yet you're still going to be learning a lot today. So let's get to it. In the A block, I just want to sketch the model of poker on the screen. I just want you to get a sense about what the game is that we'll be playing. I also want to give you a sense about how we infer the uninformed player's beliefs from observed actions through Bayes' rule, which is the foundational truism underneath all of conditional probability. What I believe about you is a function of both exogenous terms, like nature, and endogenous terms, like your own sense of strategy. That's already provocative. You might be thinking that's enough to get the lecture done with, and yet I have so much more to show you. Because in the B block, we'll talk about what separating strategies would look like, and we'll look for separating equilibria. A separating strategy is one where different types of players do different things, so that the things that the different types of players do are in fact meaningful. If I'm somebody that's planning on turning left on the road, and I put on my left turn signal, and you're somebody that's thinking about turning right on a road, and you use a right turn signal, then what turn signal a third party sees is informative. If turners left use the left and turners right use the right, then that's a meaningful signal. Now, it seems like that ought to be the case everywhere, and yet I just drive around Champaign-Urbana all the time showing people one of my fingers, I won't tell you which, because they don't use the right turn signal when they're turning right. But that's a different story, isn't it? You'll see that the nature of poker introduces all sorts of wrinkles in the terms of what intuitive separating strategies would look like in potential candidate perfect Bayesian equilibria. I'll leave it there. And then in the C block, we'll sort of flip the switch by thinking about pooling strategies where the two types of the players do the same thing. This gives the opportunity for somebody with a bad card to mimic somebody with a good card. If you're somebody with a good card and you play as if you have a good card, and I'm the version of us that has a bad card, but I play as if I have a good card. Intrigue, mimicry, meaningless signals. If everybody in the world is doing the same thing, then you can't really draw any inferences beyond what you knew about the exogenous probabilities about the world in the first place. Oh man, We're going to be hitting a lot of cool stuff today. We're going to be hitting a lot of cool stuff. You're not going to make any money. Don't go to Vegas. I mean, go to Vegas, but don't think that I'm going to help you make money in Vegas. Go watch Cirque du Soleil, have a buffet, stay in a nice hotel, but do not go play poker and then say, well, Professor Robert J. Carroll told me this is how to play. Don't go to the Bellagio poker room and say that, okay? Promise me you won't do that. It'll be so embarrassing. I've already embarrassed myself there myself. Well, now that this got so deeply personal, let's get started. All right, so here's the idea. Nature has shuffled these cards, and Nature shuffled these cards, all right? And I'll just give them a couple more just so you know. Alpha is happening. Alpha is happening. I know that some of you don't watch the cold intro anyway. You just like jump right ahead to the A block, which is what I would do too. Okay, so first things first, I'm going to turn off my monitor so that I really don't know what's happening, and then I'll show you what the interaction is going to look like. So this is me turning my monitor off. Oh God, I feel so much better. Okay, so here's the idea. We're each going to get one card. So this is your card. I'm just putting it in front of me for now, and I'm not looking at it. And this is my card. All right? And my card is going to be common knowledge to us both. My card is a jack. I have a jack. I have the jack of clubs, right? So this is my card. And the idea here is that we just want to have the higher card. We're basically playing like that kids game War, like whoever has the highest card. But we're doing it in a poker setting where there's a round of betting, and where you know your card and I don't. You know that I have a jack. All right? So I have a jack, which I'll just put next to me for now. And you have this card, which I am not looking at. I do not know what this card is. I do not know what this card is. Okay? And the idea is we both put in $1 to begin the game. Oh, I need to get my dollar. So we both put in $1. We both put in $1. You have the chance to win my beautiful, the only dollar I have left after buying all this recording equipment, Walking Liberty. So I'm anteing up. I'm putting $1 into the pot. $1. And you put $1 into the pot. So we both have invested $1 into this stupid game of poker. And now the idea here is you have one of two choices. You can either sit pat and say, I will stay with the card that I have and not put any more money into the pot. You can decide not to put any more money into the pot, in which case the game ends and we see who has the higher card. Your other alternative is to raise by putting another $1 into the pot. Okay, so you could say, oh, well, I'm going to raise. I want the stakes to be higher in this game. Now that I've seen my card, I want the stakes to be higher. So you could do that. And if you do that, now I still don't know what card you have. See, this is kind of the intrigue. So if you do that, then I have a choice to make. I can either fold, in which case you win the $1. I say, I'm not going to put more money into the pot. I'd like this interaction to be over. That's how poker players are. They're like, I would like this interaction to be over. So I can either fold and quit the game and let you have my Walking Liberty, or I can call by putting another $1 into the pot. I can put a second $1 into the pot so that now there's $4 total, and then say, let's see what you got. Okay? So I've got a jack, which means chances are good I'm going to call. If you bet, I'm probably going to call because jack is a pretty good card, right? So the only cards better than jacks are queens, kings, and aces, which means that you have a 12 out of 51. 12 divided by 51 is the probability that you have better cards than this. 12 divided by 51 is, you'd think I would know that, but you know who's not good at anything? So I'm thinking to myself, you have only a 23.5% chance of having a better card than I do. So if you raise, I'm probably going to call. I would encourage you now to think through what you would do if you had this card, which I don't know what it is still. I still don't know what this card is. So if you have a very good card, you probably just want to raise anyway. And if you have a bad card, then maybe you're thinking to yourself, well, what I'll do is maybe I'll bluff or maybe I'll just stay out. Remember, if you have a really bad card, you're going to lose either way. So you might want to try to bluff me out of the game by making me fold. But remember that if I call your bluff, then you're losing $2 instead of $1. Okay, have you made up your mind? All right, so let's see what you got. You had a king! This happened last time too. I swear to God, this was completely random. I would not lie about this. So you just got $2 off of me because chances are good you raised and I called. If you raised, I would have called, and now you have a king and I lost. I'm putting all this time, I'm investing all this energy into you, my wonderful students, and you don't even have the kindness to get in touch with me to tell me that you had a king and I had a jack. There is no justice in this world. There is no justice in this world. If you just sat here and you didn't even tell me, I turned my monitor off and everything like a really classy guy, and now this is what happened. Such is the life of a poker player, though. Injustice happens. I have to do what I think is best in expectation. I lost this hand, but I did the right thing. That's what makes gambling, right? Anyway, let's talk about how to encode the game of poker. All right, so let's talk about how we would encode the interaction that we just talked our way through, okay? So what I'm going to say is at the beginning of time, nature gets to make a move. The shuffling of the cards gets to make a move. Nature gets to make a move. All right, so I'm going to put nature right in the middle of the screen. You'll see why in here in a second. And you come in one of two types. You can either have a high card or you can have a low card. All right, we'll just say high and low, where that means sort of respective to the card that I have. Right, so high is a better card and low is a worse card. And we'll say that you have a high card with probability alpha, which falls somewhere strictly between 0 and 1, and you have a low card with probability 1 minus alpha. And I just want to reinforce the idea that alpha here is exogenous. Alpha is determined by the shuffling of the cards. Alpha is determined by nature. Nature is the tosser of coins somewhere out in the ether. Nature is the god saying who has a high card and who has a low card. It has nothing to do with the strategic choices made. Nature is done by nature. So if I have a really good card, like a jack, then alpha is something pretty low. And if I have a really bad card, like a 2, then alpha is really high. Now remember, what's happening that's unique in a signaling model relative to the other models we've seen so far is that you, the informed player, get to move first. So irrespective of what type of card you have a choice to make. So from your 2 decision nodes, you can either stay and decide not to put any extra money into the pot, right? So if you stay, then we go right to a terminal node. That means that the game ends. I don't have any betting privileges here other than to call your bet. So we have 2 terminal nodes. At one of them, you have a high card and the game is ended, which means that you win. You win the smaller pot. You will get $1 and I will lose $1. Conversely, over here in the world where you have a low card, if you have a low card and we end up at the end of the game, then you lose the $1. So -1 happiness points for you and +1 happiness points for me. So here is the one where you win the small pot, and here's the one where you lose the small pot. Okay? Your second alternative is to raise. You can put some extra money into the pot. You can put the extra $1 into the pot. And if you raise, then I, player 2, have a choice to make. All right? So we'll have player 2's decision nodes come after you raise. The problem is, I don't know what card you have, and so these 2 decision nodes are linked in an information set. I wish I knew what card you had, but I don't. I'll just work through my choices first before we talk about beliefs. So once we get to my decision nodes, once we get to player 2's decision nodes, the uninformed player, the receiver of signals, how many ways can I repeat the same thing? So once we get there, then I have one of 2 choices. I can either fold, in which case you win $1 for sure, and I lose $1 for sure. That's kind of the whole point here, is that if I fold, you get $1 for sure, and I lose $1 for sure. There's no intrigue if I fold, you just win. Notice that you win if you have a high card, and you win if you have a low card. That's what folding just means. I quit, you win automatically. I don't know how much poker you've played. You know what's a really good way to be a bad poker player is teach game theory. Everybody thinks I'm like good at poker. First of all, with this face, do you think I'm going to be good at poker? This is what I look like when I have an interesting thought. Yeah, nobody knows when I have a good card. But also, like, when people play the thing that I think isn't the correct thing to do. Don't act like you're not going to miss it. If people do what I think isn't the correct thing to do, then I get really angry. You know, oh, you won just because of luck. Because it's a game of luck in part, you idiot. That's me, not you. The other thing I could do is I could call your bet. I could say, you know what? That's fine. I'll put in another $1. Here's another $1. Let's see what you got. So if you have a high card and I call, then you win 2 happiness points and I lose 2 happiness points. Okay, so that means that you win a bigger pot. But if you have the low card and I call, then you lose 2 happiness points and I win 2 happiness points. You lose at that point in time. So this is the entire game. We have nature, the informed player. If the informed player stays, then the game ends. And if the informed player raises, then the uninformed player can either fold or they can call. If the uninformed player folds, then no matter what, 1 happiness point minus 1 happiness points. And if there's a call, then the high type is happy and the low type is sad. So this is the world's simplest game of poker, and yet it's going to be enough to give us some fits. One reason for that is that we haven't talked about one of the most intriguing parts of this model, which is my belief that you're the high type, conditional on having seen you raise. Right? So in previous versions, I haven't been able to condition my beliefs on what I've seen you do because the uninformed player has moved first so far in our incomplete information models, or it's been a simultaneous move game. Here, I have a chance to learn. I have a chance to see what you did and figure out what I think that means as a function of what strategy I think that you're playing. You'll see what I mean as the lecture goes, but part of this is going to be just a matter of seeing Bayes' rule, which is a really important result that everybody ought to know, even though we're not going to be able to get into it in excruciating detail today. It's a really important way to say, I had a belief about something, then I got a new data point. How do I update what I think I know now as a function both of my prior beliefs and the data point that I got to see in the form of your decision? That's interesting, right? I mean, this is like hundreds of years of philosophy of science before I get too deep in, I don't mean to trivialize Bayes' rule. This is a pretty big deal. What I'm going to do is I'm just going to make myself a little scratch pad that we'll use throughout. We'll say that I think that you have a high card conditional on you having raised with probability mu. So I'll put a mu next to my decision node where it's like my belief that you have a high card, we're in this world, conditional on you having raised. Okay? So with probability mu, that's my endogenous belief that you have a high card conditional on having seen you raise. With probability mu, I think we're here. And with probability 1 minus mu, I think we're here. Mu, 1 minus mu. It might be alpha. It might be 1. It might be 0. It might be anywhere in between. If mu is 1, then I think we're here for sure, and I'm probably going to fold. If mu is 0, then we're here for sure, and I'm probably going to call. But what I do otherwise is going to, if we have intermediate mu, then my decision might be a little bit more nuanced. Let me show you the formula for mu, which we'll be employing throughout whenever we have the chance to. You'll see what I mean once we get to the pooling strategies. So the formula for mu is what's called Bayes' rule. It's a conditional probability, and it's just going to be a fraction. And so the probability that you have a high card, conditional, that's what this little slash means, conditional on you having raised. Right? That's my belief. That's my conditional belief. And so in the numerator, I'm going to have 2 terms multiplied together. My prior belief that you have a high card, right? So that's called a prior. So that's the probability that you just have a high card outright. We've already discussed that. That is alpha. So the probability that you have a high card is just alpha. That's the exogenous probability of a high card. Times the probability that you raise conditional on having a high card. Right? That's going to be a part of your strategy. We don't know that just yet. That's going to depend on what choices you're making. Right? So if the high type is always raising, then that will be 1. If the high type is always staying, then that will be 0. So we have this alpha, which is determined by nature, and this conditional probability of you raising conditional on your type, which is determined by you and what strategy you're playing. So that's the numerator. The denominator goes like this. It's the same thing as the numerator. The probability that you have the high card, that's still just alpha, times the probability that you raise conditional on having a high card, that's still an empty box right now. We haven't defined what that is. That's going to depend on which strategies you choose. But to that, we will add the same idea for the low type. We'll have the probability that you're the low type, which is just 1 minus alpha, times the probability that you raise conditional on being the low type, which again is we'll leave that blank for now because we don't know that. That will depend on your strategy as well. A strategy for you is what you would do if you had a high card and what you would do if you had a low card. And that's what's going to give us these second parts of each term in this Bayes rule expression. So just as an example, Suppose that if you have a high card, you raise, and if you have a low card, you stay. That makes sense. Well, if that's the case, then my new belief isn't going to be alpha anymore. It isn't going to be alpha. It's going to be alpha times 1, because that's the probability that you're raising conditional on having a high card. We just said the high type raises. Plus alpha times 1, the same thing as before, plus 1 minus alpha, the probability of the low card, times, well, what's the probability that you're raising conditional on you having a low card? We just said that if you have a low card, we're positing that you stay, which means that's 0. Which means that our fraction winds up being alpha times 1 over alpha times 1, which is just 1. Suddenly, if the high type of you is raising and the low type of you is staying, then even though I don't know what card you have, I know what card you have. I draw the inference that you have a high card. You can work the same thing in reverse to see that, mu would be 0 if the high type of you was paradoxically staying and the low type of you was raising. Throughout the analysis, what we're going to be doing is proposing a strategy for you, figuring out what that has to do with my beliefs, and then figuring out what I would do in that context. To that end, our life will be quite a bit easier if we just think through what players' 2 best response is as a function of mu, as a function of their beliefs. So let's work that through real fast. So you'll notice that my expected utility of folding, well, with probability mu, we're in the world where you have a high card, and if I fold, I get -1, happiness points, /dollars. I'm risk neutral. And with probability 1 minus mu, you have the low card, and if I fold against somebody with a low card, it's still -1. So it's mu times -1 plus 1 minus mu times -1, which is just -1. -1. So I get -1 for sure if I fold. That's the whole point, is that if I fold, I don't have any risk in my life. I just get -1 happiness point. However, my expected utility for calling has a little bit more nuance in it. So with probability mu, you have the high card. And so if I raise, then I lose, and I lose $2. So it's mu times -2 plus, well, with probability 1 minus mu, you have the low card, and if I raise, then I win $2. That's pretty great. So 1 minus mu times 2. If you work that out, my expected utility for raising is 2 minus 4 mu. You'll notice that if mu is 0, so that I think you have the low card for sure, then I get $2. And if mu is 1, so that I think you have the high card for sure, that's the -2. And if mu is intermediate, then my expected utility lives somewhere in between. So let's just figure out when I would rather fold, when I would rather call, and when I might be indifferent between the two. So I'll prefer to fold. I will strictly prefer folding over calling if -1 is strictly greater than 2 minus 4 mu, which works out to mu is strictly greater than 3/4. So if I'm pretty sure that you have a high card, if mu is strictly greater than 3/4, if my belief that you have a high card conditional on you raising is above 3/4, then I'll fold. 3/4 is the belief that it takes for me to fold. So if mu is strictly greater than 3/4, then I fold. If mu is strictly less than 3/4, then I call, right? So if I don't think it's very likely, although notice that at 50-50, I'll call, thank you very much. Why would I call at 50-50? Because folding isn't free. Folding means I lose $1. So if mu is strictly greater than 3/4, I fold. If mu is strictly less than 3/4, I call. And if mu is exactly equal to 3/4, then I could fold, I could call, or I could mix, right? I'm indifferent, which means I could do anything there. So that decision rule is going to be an important part. We've handled backwards induction. The problem is we don't know mu just yet. But if we knew mu, if we knew the belief, which will be a function both of my exogenous belief, alpha, and your strategy, once we know mu, we'll know what I will do, and then we'll be able to work through the rest of the game. So that's poker, that's Bayes' rule, and that's player 2's best response in the context of this, with a conditional probability, a conditional belief of what kind of cards you have, not just based on how nature shuffled the cards, but also on how you decided what to do in response to nature. All this in crispy 4K. Not so bad, right? Well, we'll see how that is over in the B block once we start to talk about how to analyze this. See you there. One thing with the Funky Poker lecture is it's not quite so easy for me to do the usual magic. The magic isn't quite the same here in poker, right? I mean, we already sort of had to do this one time, and I didn't have a monitor to check my aim. So we'll see how it works this time. I'm going to do like a no-look past this version. Ready? Here in the B block, I want to talk about separating strategies. I don't even know what is this? What is this? Why didn't I do, well, because that looks stupid. No, I actually made the right choice. All right, so here's the idea. A separating strategy is one where different types of you do different things, right? So you separate. In a separating strategy, signals are meaningful, okay? So when I say a signal is meaningful, what I mean is I, the uninformed player, will be able to improve my estimate. I will no longer be stuck with just an alpha sense about what you're doing. I'll have a crispier, boy, crispy is just the word of the day. I'll have a crispier sense about what you're doing, okay? You'll see what I mean here in a second. So let me just cue the game back up. Wing! What does wing have to do with anything? So there are two potential ways for you to play a separating strategy, and we'll study them both in turn. In perhaps the more intuitive version, the high type of you might raise, and the low type of you, oh boy, here we go. The low type of you might stay, right? So this is very much an 8-bit bad guy kind of thing. And I'm losing my aim. Just keep it spread. There we go. So just imagine for now that the high type of you said, oh, I have a high card. I will try to get more money off of this bald idiot. And imagine that the low version of you said, oh, I got a really crappy card. I'll let the bald idiot have his fun for now, and then I'll get him later. That would came out a little bit ominous. So you're separating. Different types of you are doing different things. That's what I mean when I say separating. I mean different types do different things. So what we do when we analyze a game like this is we begin from a positive behavior like a separating strategy where the high type raises and the low type stays. We propose that strategy. We then figure out what that means for mu. We then figure out what that means for what player 2 would do. And then we figure out if either type would like to deviate conditional on what player 2 is doing. So that's going to be the formula throughout. The formula is going to be positive strategy, compute the mu, figure out what A2 ought to be, and then figure out if either type of player 1 wants to deviate. Let me show you what I mean here. So now that we have proposed a strategy, we have proposed that the high type, right, this is a pure strategy, the high type raises with probability 1. The probability that you raise conditional on being the high type in this strategy is 1. And the probability that you raise conditional on being the low type in this strategy is 0. Right? You're playing both types of you are playing pure strategies. Let's think through what that means for mu. Let's think through, and this is the example we already did, let's think through what that means for mu. So let's hone in on Bayes' rule and compute our mu. So remember, we just said that the probability that you raise conditional on being the high type is 1, which factors into this equation 2 times, once in the numerator and once in the first part of the denominator. And we just stated that the probability in this strategy that you raise if you have a low card is 0. So we have alpha times 1 plus alpha times 1 plus 1 minus alpha times 0, which is just 1. So now that we know that mu has to be 1, I'll label the game accordingly. Mu is 1, which means I think that we're here for sure, and I think we're here not at all. I have a completely precise belief that this is the node that I'm making a decision at. I know that we're here. Why? Because you're not playing an especially sophisticated strategy, right? The only way that we hit this information set is for the high type to take us there, because the low type never comes here. The low type never comes here. We never get here. So if we get here, then I know we're here for sure. Okay? So mu is 1. And 1 is strictly more than 3/4. Right? Mu is strictly more than 3/4, which means that there's not a whole lot of ambiguity about what I'm going to be doing. I'm going to fold. Why? Because if you walk in and say, I don't know what my cards are just yet, but I'm going to tell you right now that if I have a high card, I'll raise, and if I have a low card, I'll stay, and then I observe you raise, then I know for sure that you have a high card, so I'm going to fold. We don't need math for this. People play poker without math all the time and win. That's when I get angry. So there's no ambiguity. I'm going to fold. I'm going to fold. I'm going to fold. Remember, I make one and only one choice, so I fold at both my decision nodes, which is just my one information set. I fold. I folded. So what we need to figure out now is whether or not either type of you is sad about what happened and would like to deviate. Okay? So let's think about the high type version of you first. So you have a high card, and you got me to fold, which means that you got one happiness point. So what would it mean if you deviated? Well, if you deviated, then we're up at the world where you stayed if you had a high card. And if you stayed if you had a high card, you'd get the same one happiness point. So what happened got you a happiness point, and what would have happened still gets you a happiness point. So you don't want to deviate if you're the high type. The high type of you is satisfied. There is no profitable deviation for the high type of you. You're indifferent between what happened and what would have happened if you stayed, which means it's not a strictly profitable deviation, which means no deviation, which means that we're good so far. So player 2 is doing the sequentially rational thing by folding, conditional on their beliefs. And the high type is it doesn't want to deviate because if they deviate, they just get the same thing. So what about the low type of you? Well, right now, the low type of you is folding and getting -1 happiness points. Right? So whenever we get the low type of you, you fold and you get -1 happiness points. But if you deviated by raising, holding me fixed, if you deviated by raising, then you would go from -1 happiness points for what happens after you show your card after you stayed to 1 happiness point for the victory you got after I folded. So if the low type of you knew that I was folding, then they would raise. They would raise. They wouldn't stay out. You, the low type of you, has a profitable deviation. The low type of you, if they knew that I was folding conditional on seeing a raise, would raise. Because they would get 1 happiness point, which is strictly better than the -1 that they get for staying. There's a profitable deviation for the low type of you, and therefore, this state of affairs is not an equilibrium. Because the low type of you is sitting there saying to themselves, well, I got -1 happiness points and I could have tried. I could have done better because I knew that you were folding. I wouldn't be risking anything. There's no chance I'd wind up with -2 because you're folding in this strategy. Holding me fixed, you would raise. So there does not exist a perfect Bayesian equilibrium, and we'll talk about what that means once we find one. There does not exist a perfect Bayesian equilibrium where the high type of you raises and the low type of you stays, because the meaningful signal means that the low type of you is saying, well, I wish that I could have deviated. The high type of you doesn't really care. They're about where they would have been. It doesn't really matter all that much. So let's consider the somewhat more perverse version of a separating strategy where the high type is staying and the low type is raising. That doesn't seem right. That sounds stupid. But let's see if it is stupid. Let's analyze the model. So we've proposed a strategy. The high type is raising not at all, and therefore the probability of raise conditional on high is 0. And the probability of raise conditional on low in the strategy is 1. So what does that mean for mu? So let's hone in on Bayes' rule and think this through. We just decided that the probability of you raising conditional on the high type is 0. So it's alpha times 0 over alpha times 0 plus the probability of the low type, which is 1 minus alpha, times 1, right? 1. So that works out to 0 plus 1 minus alpha. That's 0, right? So I've been able to draw a perfect inference, but now I know we're never here and always here. If that's the strategy that we're playing, if the only way that we hit my information set is for the low type to raise, and then I see that I have a choice to make, then I know you're the low type for sure. Mu is 0, 1 minus mu is 1. You'll notice that 0 is strictly less than 3/4. And therefore, the sequentially rational thing for me to do, conditional on my newly updated belief, is to call. So now I'm calling. If I see a raise, I call. Now, what does that mean? Well, let's think about the high type of you. The high type right now it has a buck. They won. They won up here in the boring version where there wasn't any intrigue. They have $1 for sure. And if they deviated by raising, they'd get 2 because I'm calling. So there's a profitable deviation for the high type already, which means this isn't an equilibrium. But you'll also notice that the low type of you is shit out of luck with -2 happiness points. If you had stayed out, you'd get -1. In other words, there does not exist a perfect Bayesian equilibrium where you play the separating strategy where the high type stays and the low type raises. Those are the two separating strategies. Those are the two potential separating strategies. It was either this way or this way, which means that there isn't an equilibrium in this model where signals are meaningful. This game does not have an equilibrium where I am able to draw perfect inferences about you based on what I know you're doing. That sounds like poker to me. If you show up and play poker and always do the same thing with the same cards, then you're not going to do real well. If you fold every time you have a bad card, you're not going to do real well because you will have missed opportunities. If you're playing that first strategy where the high type raises and the low type stays, then the low type of you is missing opportunities. You ought to raise sometimes. Heck, maybe you ought to raise all the time. You're missing opportunities because if you're playing strategies such that I fold some of the time when you're raising, then the low type of you could be doing a lot better. You shouldn't be losing for sure. And obviously, if you play poker and you have a good card and you don't try to take advantage of it, and you have a bad card and you that's the time that you bluff, you're not going to be sitting at the table very long. You're going to be over at the buffet soon. You'll be at the buffet by 7:30 p.m. Cirque du Soleil, you might be able to watch both showings. By the way, if you ever go to Vegas, Cirque du Soleil is awesome. God, that's when you know you're an old person, is like you're telling people what to do when they go to Vegas that doesn't involve gambling or clubs. Now go to Cirque du Soleil and then maybe go see Wayne Newton or Penn and Teller. So we just saw that poker doesn't allow us to find equilibria where signals are meaningful. It is never the case in poker that in equilibrium, different types of cards yield different types of behavior, because then people will be able to draw perfect inferences about you and know when they ought to fold and know when they ought to call. You got to have a little bit of intrigue for poker to arise in an equilibrium. So over in the C block, we'll think about some intrigue in the form of mimicry, of trying to pretend like you're somebody else, in the form of pooling strategies. See you there. I'm not sure if you noticed, but the poker lecture is awesome, right? Oh man, there's just a lot going on in the poker lecture. So we just figured out you're not going to make any money with a separating strategy, because if you play a separating strategy, then every time you raise with a good card, you're not going to make any money. And every time that you raise with a bad card, you're just an idiot. So hopefully we can find something a little bit more interesting as we talk about pooling strategies. You know, you would have thought I would have updated by now, but nope, I'm too lazy. So it's going to be the same form of analysis as over in the B block. It's going to be propose a behavior, figure out what that means for mu, figure out what that means for player 2, and then figure out if either type of you wants to deviate. There are two ways for you to play a pooling strategy. A pooling strategy is one where both types of you do the same thing. And so it could be that you pool on raising, or it could be that you pool on staying. Let's do the first of those first. So let's propose the behavior that the probability that you raise with a high card is 1, and the probability that you raise with a low card is 1. Let's pool on raising. Both types of you raise now. High card raises, low card says, you know what? I'm throwing caution to the wind. I'm raising 2. I'm going to pretend like I have a good card. I'm going to mimic the high type. So this probability is 1 and this probability is 1, which means that we have a little bit more intrigue to work through over in Bayes' rule. So let's hone in on it. So now, the probability that I think that you have a high card conditional on having seen you raise is, so the alphas and the 1 minus alphas haven't changed. That's still just as exogenous as ever. But what's different now is that the probability in this strategy that you have a high card conditional on having raised is 1, because the high type is raising. And the probability that you have a high card conditional on being the low type is 1, because in this strategy, the low type is raising 2. So that's alpha times 1 plus alpha times 1 plus 1 minus alpha times 1, which works out to just alpha. Alpha. This is what I mean when I say that the signal is meaningless if different types do the same thing. This is a meaningless signal because even after having observed the data point of you raising, I still have the same exact belief about whether or not you have a high card. Instead of getting to go to a 1 or a 0, being able to draw an inference about you, now I'm just as confused about your card as I was before. Meaningless signal, as opposed to the perfectly meaningful signal in the B block. It's pretty heavy, right? I don't know about heavy, but it's kind of interesting how the machine works. This Bayes rule machine is magic. It was discovered by a monk in the 1700s. His name was Bayes, not his first name. His first name was Thomas. So now we have to think through two contingencies, because you'll remember that my decision rule about what to do once we get to my node, player 2, I'm just dropping deuces, right? So my decision about what to do depends on mu, and now mu is just alpha. So we have two contingencies to think through, okay? So let's suppose for now that alpha is strictly less than 3/4. If alpha is strictly less than 3/4, then I am going to call. I call at alpha less than 3/4. So if alpha is less than 3/4, if it's very unlikely exogenously that you have a high card, or if it's sufficiently unlikely anyway, then I will call. So now the high type of you is really happy because the high type raised and I called and you get $2. They don't want to deviate because they just got $2. That was the whole idea of raising, was to get an extra $1 off of this idiot. But the low type of you is like, whoa, this seems like an unforced error. The low type of you is saying to herself, wait a second, I raised and I got -2 happiness points because I got called. And if I had just stayed out, I'd only lose $1. And losing $1 sucks, but it's better than losing 2. So in other words, they would like to deviate. They would like to deviate because they didn't have a high enough alpha to play with. So you shouldn't pretend like you're the high type if it isn't very likely that you're the high type. You can't mimic high types if high types are rare. The dream scenario for somebody with a bad card is for it to be unlikely that they have a bad card. Then they can pretend like they have a good card. So in this world, if alpha is low enough that I'm going to call, then you wouldn't want to pretend like you're the high type. That's not what you're trying to do when you act like the high type is get me to fold. You're trying to get me to fold. You don't want me to call. So let's think through the contingency where mu is strictly greater than 3/4, so that it's likely that you have a high card. So if mu is strictly greater than 3/4, then my best response is to fold. Now I'm like, well, I don't know what you have because I'm still stuck with alpha, but going into the interaction, I thought it was pretty likely that you had a high card. So if alpha is sufficiently high, right? So if I have a 2 or a 3 or a 4, so that I'm thinking the chances are pretty good you have a card that would beat me, and then you have a card that wouldn't, but you raised, then I will fold. Now the high type of you isn't super happy, but they still have that 1 happiness point, and if they had stayed out, they'd still have a happiness point. So the fold gets them the 1 happiness point. The stay would have gotten them a happiness point, so they don't want to deviate. They don't want to deviate because it's 1 happiness point either way. They don't care. The high type doesn't care. But the low type seems pretty smart right now, right? Because right now the low type is thinking, well, I raised and I got them to fold, and that got a happiness point where I shouldn't have had one. In other words, if they had stayed, they would have lost a happiness point, so they don't have a profitable deviation either. So let's think that through. If alpha is sufficiently high, if chances are good that you have a high card, and both types of you raise, and I fold because I think you have a high card because my mu is alpha, then the high type of you doesn't want to deviate because they do the same either way. And the low type doesn't want to deviate because they won a buck where they were going to lose one. I don't want to deviate because I did the sequentially rational thing. The high type of you doesn't want to deviate. The low type of you doesn't want to deviate. This is an equilibrium. This is a perfect Bayesian equilibrium. So what happens in a perfect Bayesian equilibrium is the following. I do the sequentially rational thing conditional on my beliefs. My beliefs depend on your strategy and my exogenous belief about your high card. So I have to use Bayes' rule coupled with your strategy to determine beliefs. And then I do the sequentially rational thing conditional on those beliefs. Mu is strictly greater than 3/4, so I fold. And that mu didn't come out of nowhere. That mu came out of Bayes' rule and your strategy. And in that strategy, both types of you are raising. So if it's sufficiently likely that you have a high card, like if I have a really bad card, then it's a perfect Bayesian equilibrium for both types of you to raise. Notice that if mu is exactly equal to 3/4, then it's an equilibrium for you. It's an equilibrium too, because I could choose there to fold. So if I'm choosing to fold at mu equals 3/4, then that's still an equilibrium. So that's our first perfect Bayesian equilibrium in this game. You have, chances are good you have a high card, like maybe I have a low card to begin with. So if chances are good that you have a high card, the high type does what high types do, and the low type pretends like they're a high type. They do what high types do too. Now let's think about the strategy where both types pool on staying. Now what the heck does that mean for mu? Wait a second, we never hit this information set. We never get down here now. Both types, right? So the high type is staying, the low type is staying. We never get down here, which means if you work things out in Bayes' rule, we'd be trying to divide by 0, which is frowned upon in most social circles. So we don't use Bayes' rule on information sets that don't get hit. Instead, what we say is any mu would suffice. We can think through any mu here, right? So if we can find a mu where nobody wants to deviate, then we're good. And if we can't, then we're not good. Let me show you what that means in this particular context. So we can have any mu that we want. So we have to be logical. We have to poke at the model now. So suppose that mu was just a free parameter. What would it take for neither type of u to want to deviate? Well, think about it. Let's start with the high type. If we hone in on the high type, who right now is staying. So they're staying and they get 1 happiness point. If they raised, then they could either get 1 happiness point if I fold, or 2 happiness points if I call, or something in between if I'm mixing. But notice with me that the only way that the high type wouldn't want to deviate is if I was folding for sure. Because otherwise it would be some mix of 1 and 2. And any such mix is strictly better than the 1 that the high type is getting for staying. The only conceivable way that the high type would not want to deviate from staying is if I, player 2, would be folding for sure. That means that mu has to be strictly greater than 3/4. So we have to choose a mu such that I fold. That's the only way that the high type of player 1 would conceivably want to stay, is if I was folding, if they were indifferent like before. But now notice with me that if I am folding for sure, then now the low type is thinking to themselves, well, wait a second, why am I stuck with this -1 when I could have had 1 when they folded? In other words, the thing that incentivizes no deviation for the high type is precisely the thing that incentivizes a deviation by the low type. There does not exist a perfect Bayesian equilibrium where both types stay, because in order to get the high type to be cool with that, we'd have to make the low type not so cool with that. The world of off-path beliefs, that's what this is called, is like an off-path belief. What muse would happen if the information set never got hit? That's a weird and wonderful world, and if you ever took another advanced game theory class, you'd probably spend a lot of time on what sort of beliefs seem reasonable for information sets that don't get hit. But in a class like this one, this is more than enough just to say, use Bayes' rule whenever possible, otherwise don't. For the record, on finals or whatever, I will always give you the formula for Bayes' rule. I would never not give you the formula. That isn't right. So you only use Bayes' rule when you have the chance to, which is to say if you don't have to divide by 0 to use it. So we found an equilibrium in this model though, right? So finally we hit pay dirt. We figured out that when mu is strictly greater than 3/4, so that I would fold, then both types of u raise, and that's equilibrium. The low type gets to mimic the high type and it works. Alpha strictly greater than 3/4. Alpha strictly greater than 3/4. But wait a second. If alpha was strictly less than 3/4, then that isn't an equilibrium. And we've discussed 4 possible strategies. Separating high type raises, low type stays. Never an equilibrium. Separating high type stays, low type raises. Never an equilibrium. Pooling both types stay. Never an equilibrium. Pooling both types raise only in equilibrium when alpha is greater than 3/4. And now the funding agency called. And they said, what do you do when player 2 has a good card? I don't know. Because if mu is less than 3/4, then the thing that was in equilibrium sometimes isn't in equilibrium, which means that we don't have an equilibrium. The funding agency is really pissed off at us now because they gave us all this money so that they could learn how to beat Vegas, and we don't have an equilibrium. We don't have an equilibrium. We don't have an equilibrium. Oh, I have a tummy ache. Oh, I got a tummy ache. We don't have an equilibrium. We don't have an equilibrium, and the funding agency is going to call, and we don't have an equilibrium. We don't have an equilibrium for when alpha is strictly less than 3/4. We don't have an equilibrium. We don't have an equilibrium. I can just feel it coming. I can feel all the stress coursing through my face. I can just feel it. We don't have an equilibrium. We don't have an equilibrium. What are we going to do? We don't have an equilibrium. I don't know what's going to happen because the funding agency is going to call, and when alpha is greater than 3/4, then we're good. But if alpha is less than 3/4, we don't have an equilibrium, and they gave us all this money, and this is a big federally funded thing, and I don't know what we're going to do. And oh my God, is the earth starting to shake? The earth is starting to shake. I have no idea what's going to happen. Ah! 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 Here in the D block, we're going to talk about mixing. That was the first take for the record. Thespianism. All right, so let's consider the world where one of the types is mixing. This is what's called a semi-separating strategy, where one type plays a pure strategy and another type mixes. And I know that this is scary, but you're going to do just fine. The Bayes rule machine is going to be super fun, and we're going to see that there's we're going to be like sleuths here. We're going to get to the bottom of things. We're going to figure out what you do when alpha is less than 3/4, which is like a lot of the alphas. So let's consider the world where the high type raises for sure, right? If I have a high card, I'm not going to not raise, right? Because even if you fold, it's exactly the same as if I stayed. So suppose that the high type raises for sure, all right? That sounds smart. Let's not make this complicated. But let's suppose now that the low type, instead of raising for sure, let's say that they raise with probability P. They choose some mixing probability, they raise P% of the time, and they stay 1 minus P% of the time. They're bluffing. This is bluffing right here. I mean, mimicry is bluffing, but here it's like, this is a lot more realistic. It's like sometimes if you have a low card, you jump in, and sometimes you don't. So the probability of raise conditional on the high type is 1, and the probability of raise conditional on the low type is P. They're mixing. Before we go to the Bayes rule machine, however, notice with me that the only way, per usual, that the low type would be willing to mix is if they were indifferent between what they get for staying and what they get for raising, right? The only reason that the low type will be willing to do us this favor of mixing so that the funding agency doesn't harass me, the only reason they'd be willing to do that is if they were indifferent between what they get up here and what they get down here. So notice that if the low type stays, they get -1 happiness points. And if they raise, then they get either -2 or 1, neither of which is -1. In other words, in order to get the low type to be indifferent, the only way that the -1 could be, neither of these things is -1. They can't be indifferent unless player 2 is mixing as well. So we need player 2 to be mixing. So let's work out what mixing probability player 2 would have to play. So suppose that player 2 folds with probability Q. So if player 2 folds with probability Q, then the expected utility for the low type of raising is 1 times Q, right? They get 1, with probability Q, player 2 is folded and you get 1 happiness point. And with probability 1 minus Q, player 2 is folded and you get -2 happiness points. That works out to 3Q minus 2. 3Q minus 2. So that if Q is 1, so that they're folding all the time, you get 3 times 3 minus 2, which is just the 1. And if Q is 0, then you get -2. And if the question is, what's the Q that renders the low type of player 1 indifferent? So in other words, when is 3Q minus 2 equal to -1? I was screaming for a reason, okay? When is 3Q minus 2 equal to -1? Well, you work all that out, and that's Q is exactly equal to 1/3. So the only way that the low type of player 1 would mix, which is saving my ass right now because the funding agency wants to know what happens when alpha is less than 3/4. The only way that the low type would be willing to mix is if player 2 was mixing, and in particular, if player 2 was mixing with folding 1/3 of the time and calling 2/3 of the time. So we figured out the conditions under which player 2 is willing to mix, but we still don't know P, their mixing probability. We still don't know how often they will try to raise. We just know what it would take for them to be willing to do that. That's a necessary condition for an equilibrium. We need to find P. If we find P, then we're done. We're good. Because we found Q. We know that the high type is going to be raising for sure. We know what player 2 would have to do in an equilibrium. They have to fold with probability 1/3. And now the question is, what's this last mixing probability? What is the P? What is the P that saves the day? That's a weird sentence. In order to find the P, we will leverage the fact that player 2 would be willing to mix only if they were indifferent over their options. Player 2 only mixes if they're indifferent. Otherwise, they would play one thing or the other for sure. They would play a pure strategy. Player 2 is only willing to mix if they're indifferent, which means that we need to figure out which mu would make player 2 indifferent. We've already figured that out. The only part of player 2's best response that involves mixing is when mu is exactly equal to 3/4. That's the only reason that they would mix, is if mu is exactly equal to 3/4. So suppose that mu equals 3/4. What would it take for mu to be equal to 3/4? Well, let's go to Bayes' rule. And suppose that mu equals 3/4. We need to figure out how to express Bayes' rule now that we have this new strategy. So you'll remember that the probability of raise conditional on the high type is 1. And the probability of raise conditional on the low type is P, which is somewhere strictly between 0 and 1. They're mixing. So then Bayes' rule works out to alpha times 1 in the numerator plus alpha times 1 plus 1 minus alpha times p. And the question is, under what conditions, under what p, does that equal 3/4, which is what it would take for player 2 to be willing to mix? So when does alpha over alpha plus 1 minus alpha p equals 3/4? Well, if you just work all that out, which by now, remember like in week 1 when you're like, oh my God, I forgot about high school algebra. And now here we are at week 14 and you're like, oh yeah, that's nothing. Well, not nothing, but you know what I mean. If you work all that out, then p equals alpha over 3 times 1 minus alpha. 3 minus 3 alpha. So if alpha is high, then p is high. So if it's very likely that you have a high card, then I will raise very often. And conversely, if alpha is low, if it's very likely that we have a low card, then I'll raise sometimes, but not very often. You'll notice that p is a probability. It lives strictly between 0 and 1 because it's not a pure strategy probability. It's not a degenerate lottery. So we're raising some of the time and we're staying some of the time, which means that this has to live between 0 and 1. And the question is, under what conditions, under what alphas, is p strictly greater than 0 and strictly less than 1? And you'll notice that that's when alpha is strictly less than 3/4. So in other words, we have figured out what happens as a function of all possible alphas. So let's just summarize what we're talking about here finally with a little alpha chart. So suppose that this is alpha. So I have a line that represents alpha. Here's alpha equals 0. Here's alpha equals 1. Importantly, here's alpha equals 3/4. So for all of these alphas that are strictly less than 3/4, then we play the equilibrium that was just described. The high type raises for sure. The low type raises with probability alpha over 3 times 1 minus alpha. And player 2 folds 1/3 of the time. And importantly, the equilibrium belief mu equals 3/4. Okay? So that's for all of these alphas. So that's the equilibrium. You might call that the bluffing equilibrium. If alpha is strictly greater than 3/4, then we just play the equilibrium where we pool, where the two types of player 1 do the same thing. They pool on raising. The high type raises, the low type raises. The belief, mu, is just equal to alpha, and player 2 folds. And if alpha is exactly equal to 3/4, then either of those is possible, because you'll notice that if alpha equals 3/4, then p works out to 1, which is just the pure strategy, like limiting case of the mixing probability we just described. That's enough to get you thinking pretty hard, right? So remarkably, what makes poker poker is that you don't do the same thing every time. You don't reveal everything there is to know about you based on your behavior. You have to play strategies that either involve mixing it up through bluffing or just pretending like you have the high card through mimicry. Those two things sound very pokery. In particular, if alpha equals 1/2, so that we're at a maximally 50-50, if nature seems as natural as possible, so that I really don't know that much about your card, then you bluff. If alpha equals 1/2, so that I don't know anything about you, then you raise 1/3 of the time. So the less that I know about you, the closer your bluffing probability is to 1/3. If I know that you have a bad card, you bluff less often. If I know that you have a good card, you bluff a little bit more often, until all the way up to alpha equals 3/4, and then suddenly you just start mixing, you just start raising all the time. There's no bluffing. Now you're just acting like you have a high card, because you know I'm going to fold for sure. Really, the only discontinuity in the whole model, the only sort of switch that gets flipped, the only little sudden shift in the model, is when player 2 switches from mixing at the folding probability is 1/3, to suddenly they just fold for sure. So that's poker. Pretty easy, right? Now write down the model for 5-card draw and you'll be just fine. So what did we talk about today? Well, on a prima facie level, we talked about poker. We talked about the world's simplest version of poker. There were two types of cards that you could have and two kinds of actions that you could take, and then I observe one of those actions and I could make one of two choices. And so in a prima facie sense, we didn't really discuss anything very important. But as was discussed in the intro for today's movie, which seems like forever ago by now, I'm sure, we discussed the fact that poker is an interesting analog for all sorts of interesting political processes, and as Karl von Clausewitz put it, for political processes as important and weighty as war. In that sense, if you're able to understand a model like this simple model of poker, then you're able to extrapolate lessons to interesting political phenomena, or there's just some interest in understanding poker for its own sake, which I think is worth doing. Poker's a fun game to play. Chances are good that if you find the right set of friends, that you might have a periodic poker night, and it's nice if you come armed with some game theoretic lessons from your game theory professor. But along the way, we talked about some really interesting phenomena that aren't pokery necessarily, but are related just to the fundamental aspects of the human experience. It was the first time that we got a chance to talk about what it means to learn from data. What does it mean for you to have an initial belief about something, and then observe something, and then have a chance to update your beliefs, right? So we saw that it's not very smart for you to just say that alpha is your belief about the world the entire way through. You ought to update your beliefs based on the things that you see. But that doesn't necessarily mean that you have to suddenly update your belief to just zeros or ones. You can update your beliefs to something intermediate. In a sense, that's a really important analog for life, overpromising, in the sense that you probably have some probabilistic beliefs about all sorts of important things, like what the state of the world is, who ought to be the candidate that wins, what sort of trade policies should we enact, all the different things we've had states of the world about. Or just less importantly, you might have probabilistic beliefs about whether it's going to rain tomorrow. But you shouldn't make a bet about whether it's going to rain tomorrow, today, before you have the chance to look out your window and see if the rain clouds look ominous. You have a chance to observe signals from nature, and in strategic situations, you have a chance to observe signals from your opponents. That requires learning from data in a principled way. And Bayes' rule is the most principled way to learn from data. Perfect Bayesian equilibrium reflects a new standard of rationality for us because now it isn't just about best response, or even just about sequential best response. Now it's about sequential best response conditional on appropriately defined beliefs. This is the nexus of everything we've been talking about. Information and time and strategy come together in this really unique way where I believe things based not just on my prior beliefs, but on what I observe from you, conditional on what your strategy is. And then we have to think about what that strategy is as a best response to what I would do, conditional on the beliefs that I came up with based on your strategy. That somehow is the thing that I intended to say. That's the nexus of this entire course. We talked about rationality, we talked about uncertainty, we talked about bargaining, we talked about optimality. And then once we dug into game theory, we talked about strategy and best response. We then enhanced that model by talking about time. And then we enhanced that model even further by talking about information. Once we take rationality, decision-making, high-end decision-making, what do people do if they have the chance to be creative and competent? What do they do when they face risk in von Neumann and Morgenstern accepting ways? What do they, if that's our animation for the individual level behavior, and then we embed them in strategic environments. And once we've embedded them in strategic environments, we hypothesize that they will act in accordance with Nash equilibrium. They will find best responses. That was hard already, right? And then we said, well, we will rule out incredible equilibria. We will take candidate entry or ultimatum or pivotal politics or any other sequential game, extensive form game, and say there are many equilibria of these models, but we will only worry about those equilibria that take time seriously by focusing on sequentially rational, backward induction respecting strategies. And that was a chore in its own right? I mean, so backward induction is pretty intuitive, but conceptually, that's a pretty big development. And yet that wasn't enough because there's this other interesting aspect of our lives in the form of incomplete information. Some strategic players know things that others don't. This introduced an entire new dimension of uncertainty. And so today's lecture is the nexus of all of that. It starts from week 2 and it ends at week 14. I mean, in a sense it sounds trivial. I just summarized the entire course in a couple of sentences. I just talked about what the bottom of the mountain was and what the top of it's going to be. But you know by now that every step of that mountain has been pretty arduous, including these last few steps that we took today. It's been a lot of hard work, but I hope that this view has been worth it. And you'll see next week that there's even a little bit more that we can see if we just sort of look upward to the heavens once we get to the top of the mountain. Or maybe it's a matter of looking inward, but we'll talk about that next week. But the skeptics among you might be thinking that what just got showed to you and called the top of the mountain isn't worth it, because this model of poker, though interesting, has nothing to do with the games of poker that you may have played with your friends or your family sometime. Nobody ever plays poker with just 2 cards. Nobody ever plays poker where there's just one round of betting determined by one player. This doesn't seem very realistic at all. And it's with your very natural skepticism in mind that I'd like to conclude with a provocative thought. In a class like this, we focus a lot on how to solve models, how to find the equilibria of a game that's been handed to you, right? So I write down a poker game and I say, find the equilibria. I write down a prisoner's dilemma and I say, find the equilibria. I write down rule of law or ultimatum or pivotal politics or bargaining model of war and I say, find the equilibria. But those models don't come out of nowhere. These models don't come out of nowhere. They come out of somebody's head. They come through scholarly dialogue. We refine these models by arguing about them over time. These models don't come from nowhere. These models are stories written by people. And there's a real art to modeling. It's the fun part. As you know by now, the solving isn't necessarily the fun part. The modeling is. The getting to go to a whiteboard and sketching through what you think are the essential core features of an important strategic interaction. If you ever walk around the halls of the political science department, you'll see people mumbling to themselves and occasionally walking back to a whiteboard to write down one letter on a board. And you don't realize that that letter took hours of effort, hard, intense work to figure out what parts of a strategic interaction are worth complicating our models and analysis for. What's worth it? What are the features that are worth including? So in a sense, one reason to want to be parsimonious with our models, to include only what is necessary, to have a preference for simplicity, is that the analysis can become quite cumbersome if we include too many things in our models. Parsimony is a virtue because we don't want to make life any harder for ourselves than it has to be. But if that's the point of view that makes us want to have parsimony, then the fact that it's getting easier and easier and easier to perform complicated proofs through computing suggests that we don't have to compromise because, yeah, it's really tedious for us to do hard analyses, but we can outsource that to the computers. Eventually, it will be very easy for us to do analyses, game theoretic analyses, or even just real hardcore mathematical proofs by virtue of computers. And so maybe we don't have to put up with simplicity. Maybe the top of the mountain isn't where you think of the top of the mountain is because we are less constrained than we may have thought that we were. That's a very interesting thought to think, and it suggests that our human limits are only the limits of our creativity, rather than the limits of our ability to analyze or to put up through tedium. However, there are other reasons to favor parsimony over complication that aren't just related to the tedium of analysis of complicated models. One reason to want to write down a simple model is that it has a better chance of teaching you general lessons, generalizable lessons, lessons that you can transport from one context to another. There are many different kinds of poker. None of them are like the kind that we played today. Some of them involve 5 cards, some involve 7 or 9. Some involve cards that you have in your hand and then community cards like Texas Hold'em. Some of them involve cards that everybody gets to see that you have and cards that you have secret. Some of them involve trying to come up with the worst possible hand, like Raz. There are many different varieties of poker. There's no way that I could write down every possible kind of poker in a game theoretic model and expect to teach you a lesson that you can remember. It's true that the computers that we would be able to come up with would be able to come up with incredibly complicated equilibrium conditions. We could come up with an equilibrium that's pages upon pages upon pages of computer output. But it's probably frowned upon for you to take that binder of strategy over to the poker room at the Bellagio. You have to come up with succinct, memorable lessons to be able to transport to whatever game of poker you find yourself in. When I show you a model of poker that's so simple that somebody would laugh at it, it's not because that's how I think poker is, or even how I think poker ought to be. It's because I have faith that whatever lessons I teach you with this simple model will be something that you might be able to transport because you are familiar, because you are wise, because you know when to apply particular lessons in any particular context which I would have no hope of being able to predict the conditions of. I don't want to tell you how to play my poker. I want to show you lessons of my poker that I hope you'll be able to transport to your poker. And it's not just poker. Not all wars are the same. Not all elections are the same. Not all legislatures are the same. Not all countries are the same. Not all Earths are the same. It's an act of hubris to think that we're going to be able to come up with characterizations of all possible strategic interactions and all of their highly detailed beauty, because for starters, there's already way too many of them, and secondarily, we have no idea what's coming in the future. It would be an act of hubris for us to think that what our goal ought to be is complete characterizations of very detailed models. That would strip away the humanity, strip away the fact that I'm trying to teach you a lesson with a fable. And this model of poker that I showed you today is as fably as they come, because even though it has nothing to do with real poker, it has everything to do with how I think maybe you ought to play poker whenever you find yourself there. Just the same way that the fox and the grapes involves all sorts of unrealistic assumptions and simplifications, so too does this model of poker involve all sorts of unrealistic assumptions and simplifications. But that doesn't mean that you can't get a punchline out of it, that you can't get a moral of the story, like, hey, don't play separating strategies. It doesn't take a complicated model for me to tell you that. It takes just enough model. And anything that goes beyond that is something that might obfuscate that simple truth. Our goal in this discipline of ours is to try to come up with memorable, succinct depictions of what's going on. Too much detail, and we won't be able to generalize. Too little, and people won't be able to learn lessons. Like a cinematographer, we have to know when to choose a lens appropriate for a close-up and when to choose a lens appropriate for a wide shot. More often than not, my preference is to show wide shots because those are things that will allow you to generalize. It does mean that you aren't going to be much of a historian. Historians love details. They want to make sure that they get one or some small set of things just right. But my goal as a political scientist is to be able to liken one thing to another. That's part of the science of patterns. Our goal is to say that two different things are similar to one another in the sense that they might be modeled like a simple model of poker. It's been week one all along. I know that it feels complicated as you're slogging your way through the analysis, and that's not any fun, and I'm really sorry about that. It isn't fun for me either. What's fun is trying to figure out which things are similar because they can be related back to the same fable. And I'm quite confident that today's fable is something that many things could be related to, whether it's different kinds of poker, different kinds of wars, or different kinds of political behavior in other contexts. I hope that you'll agree with me. I hope you've developed a taste for that simplicity that is complicated, for that complication that is simple. I find myself getting worked up about it. I don't know why. Because it's a real balance that you have to strike, not just as students in this class or not even as undergraduates that are political science majors. Figuring out how hard to grip what you think may be true. It's not a simple task, and it gets more complicated as you get older. That's why it's really important that we have these simple tools for introspection. It's really important that we're able to work our way through these things and hope that we've gained something from the analysis, not just the simple punchlines, but also an improved understanding of things and more faith in ourselves. I hope that you have more faith in yourself as an analyst now that you've seen things that have maybe embarrassed you by how tricky they are. I hope that you feel a little bit more humility, but also a little bit more empowered. I hope that this stupid model of poker, this top of the mountain, is something that's made you feel like it's worth it. And if you don't feel that way just yet, then this next problem set will be my last chance to make sure that you feel that way. I really hope that you feel that way by the time that we're done. So please try your hardest. I'm begging you, try to see this for more than just poker, but also for less. I'm sure you're not going to miss all these contradictions, but that's just how it goes sometimes. So thanks for tolerating that. Thanks for working really hard on this problem set. Thanks for climbing this mountain with me. But most importantly, thanks for watching. Ah!